Okay, now we will discuss about Gauss elimination trap. So you have already know what is Gauss elimination, but there are some traps there, and we have to know what is the traps in Gauss elimination. The first traps is division by zero or near to zero. So suppose I have this equation, linear equation, and then you can see that this pivot should be x1, but x1 have the zero coefficient, so I cannot use this first row as the pivot to change the second row and third row become zero or become a triangular matrix. So what is the solution here? We can change the position of the equation, so you can put the first row into the second row or third row. So you can change this between first row and second row, or first row and third row, and then you can do the Gauss elimination. And then the other traps is rounding error. So here, suppose you see the previous example in Gauss elimination which I give in the last or the previous video, that we use 4 significant digit or 4 digit after the comma, after the decimal place, 4 digit for decimal place. But here if I use only 2 digit of decimal place, so there is a rounding, then the result will be different. Suppose here the exact solution should be 7.85, but I will have the solution in 8.36. so this is a huge difference here. When you take a lower significant digit, then it will change, the solution will change. And this also in equation 3 we can see that the difference is 0.3 between the exact and Gauss elimination solution. So be careful with rounding error. And then the other trap is ill condition matrix. So as you already know in the beginning of this topic about simultaneous linear equation, I show you some condition of equation or matrices, which is we can say that it is L condition if the function or the equation is near to each other, or even just the same or equal or parallel like this. So we cannot find the solution easily in here. There is no solution here. This is many solution, and this well, there is solution, but it's not clear enough. So what is L condition matrix? Suppose you have these two equation. You do this in okay, you do this in unknown variable elimination. So if you have two linear equation, then you can change into this so that you can eliminate not the elimination. Okay, This is in graph method, I'm sorry. So in graph method, if you have two equation, you can draw the graph by changing this into the equation into a linear equation, which you know before, that this is suppose you familiar with y equal to mx plus c. So this is the y, this is the m or gradient, this is x, and this is the c intercept. You can change your equation into this form. And then if you have ill condition matrix, you can see here that all the gradient, this is almost the same, the gradient is similar, this is equal and this is equal. So if you have two equation which has same gradient, then you can write like this, that the gradient is just the same or similar or equal. Then you will have this one. So you a11 multiplied by a22, a12 by a21 and subtract each other equal to 0, right? So what is actually this is this one is a determinant. So why, if we have the determinant equal to 0, then our matrix will be an ill condition matrix. But if we have this condition, the third condition, then we have no solution, we cannot find the solution. But if we have these two conditions, we can find solution, we still can find solution, even though it is not so obvious. So this is the reason why determinant equal to 0 makes your matrix ill condition. But actually you can measure your condition of your matrix, is it ill or not, by also using condition number. But we will not discuss here, we just discuss the determinant only. So if the determinant near to 0, it means that this condition, then the variable x1, x2 and xn, if we change this variable slightly, then the equation will change drastically, or we can say that this is ill condition. As you can see here, the example of this condition, we just change the rounding error, we just change the rounding, we use the two significant digit, but the result here is totally different if we use 4 significant digit. So actually the system is ill condition, it means that the determinant near to 0. So this is the example of ill condition. So be careful with significant digit. And then determinant is very important to see your condition of your matrix. So how to find determinant in huge linear equation? So if you have many number of linear equation, then finding D is complex, it's consume time. And then how to simplify to find the determinant is that you change the matrix into triangular matrix. If you have triangular matrix, then the determinant is just simply the multiplication of the diagonal, like this. So if you have huge linear equation or huge matrix, you change into into upper triangular or lower triangular matrix, and then you just simply calculate the diagonal element, then you will have the determinant. So now we will discuss how to avoid the trap. How to avoid the trap is, first, use high precision number. Suppose you can use 10 digit uh, 10 digit decimal or 5 digit decimal. Of course 10 digit decimal is better than 5 digit decimal, and so on. So use high precision number as much as possible. Well, if you do hand calculation, of course this is difficult. For hand calculation, well, 2 digit maybe is enough, but for computer calculation, use high precision number as possible. And then the second way to avoid the trap is change the order of the equation. So suppose you have this equation, you can see that this can be trapped into a division by 0 because this coefficient is very small, so it can be division by 0. Then how to do that? You just interchange the order. So this diagonal element must not 0 or near to 0. So if you change, then you have the diagonal is not near to 0, then you can solve this equation. And then the last way that you can do is by doing scaling. Suppose I have this linear equation, and then better to change the equation, or we normalize the equation so that the the coefficient, the maximum coefficient will be equal to 0. This is 100,000, so we have to change this, so it will become 1. Then I do the scaling, and the result is like this. And be careful that it can be divided by 0 because it is in the diagonal, so we have to interchange the order. It's become like this, and you can see the diagonal is not 0. Then we can find the solution of this equation. So this is how you avoid the trap. At least you can do these 3 ways.